Hi everyone, welcome back. This is David Singletary again. Now we're going to dig into data types in more detail. We briefly touched on the basic numeric types, character types, vectors in the last module. In this module we'll talk in more detail about those, and we'll also talk about some of the more complex data types and how we manipulate those with R. We mentioned vectors in module 1. Vectors contain the same data type. They're similar to arrays in other programming languages. We can create them with a single value. If we want to see the length of a vector, we have a length function we can call to find out how long it is. So in these examples, we're seeing that we're creating a vector called 5 that contains just the number 5. And when we display it by typing in the object or variable name here, we see the contents, just the single element, the number 5. Is it a vector? Well, we can run the is.vector function and pass that 5 to it as a parameter to verify that it is indeed a vector. We get true returned from calling that function. If we want to see how long it is, we use the length function. We pass that vector as a parameter, and you see that we get 1 returned for the length of the vector. So if we do this in R, 5, use the assignment operator and you give it the value 5. Now this is a number, it's not character, but it's the numeric value 5. To display it, we just type in the name. Remember, we can use print, and we can also use cat, but it's just as simple just to type in the variable name itself, 5. Is it a vector? Yes. True. And how long is it? It is 1 element long. Now let's look at some more vector examples. We can do simple numbers. For instance, the sequence 1 through 5. Notice we're using the C function here. We can do letters or character data. Notice that we're using single quotes to enclose each of the characters in this. The length for each of these vectors is 5. And this leads to another interesting little illustration of our vector behavior. If I create one of these vectors, let's call it NV for numeric vector. Remember, I can do a range 1 through 5. I can use that C function. And you notice these are all integers. They're all basically whole numbers. I can do this. Create it with floating point values using a decimal point. And you notice I have floating point values. What if I mix them? NV, C, integer 1, 2.2, integer 3, 4.4, and integer 5. What does R do? It converts them all to floating point values. Remember, vectors are like arrays. R wants similar data types stored, and so it converts them to be consistent. We saw that we could do character vectors. Character vector CV, C, A, B, C. You notice it converts to double quotes. You notice it converts to double quotes. Remember, you can use single or double quotes. You can even mix them between elements. Single quote, double quote, single quote. R doesn't have a problem with that. It converts them to double quotes in that case, but you can't mix them within a pair. So CV, C, single quote A, double quote, then single, double. And you see R has a problem with the A because I've mixed single and double quotes. So you need to be consistent on your use of quotes in those. What if I do this? Numeric vector C, the number 1, the character 2, number 3, 4.4, 5. So you see I've got a mix of data types here. I've got integer, I have character, I have floating point, So what does R do with this one? It converts them all to character. We'll find a lot of times R will just take the easy way out when you have a mix of data types like this and do the simplest conversion, which would be just to convert everything to a character form instead of numbers. Now, I've already mentioned that we can use single or double quoted strings for elements in a character vector as long as you're consistent with the pairing of them. You don't want to mix and match single and double. R will convert to double quoted, but it'll accept single quoted. You can see here we're checking that this vector containing the words welcome to R is a vector by calling the is.vector function. And we can also see that the length of that vector, independent of the length of the words that comprise the elements of that vector, is 3. There's 3 words in there based on the comma-separated elements. Another primitive data type we have in R are the logical data types. These are true and false values, the Booleans. We can use the entire word true and false, or we can just abbreviate it as T and F, and you'll see this a lot because obviously those are a lot easier to type in. So here we're creating this vector called all true, assigning it to the values true, true, and true. So when we display the values, you see R will print the entire word true, even though we've used the abbreviated T. Here we're mixing the values here, some true, giving it the value of true, false, and true. You can see if I do a type of, this function will display the type of the elements that the vector contains, which could be number or character, but in this case is logical because these data types are the logical types. And I display the values and you see it prints out the entire words for each of the elements. Now there are a lot of functions we use with vectors. We've seen a few of them already. The is.vector is one that we've used. There are more interesting ones that we use in the context of data science though. For instance, the sequence function, the replicate function, sorting. Length we've seen already, determining the length or the number of elements in a vector. So sequence generates sequences as indicated by the name, and replicates values. The sort function sorts a vector in ascending or descending order, so that should be apparent that we're going to provide some sort of arguments to indicate whether it's ascending or descending. And then the length, again, we've seen already, gets or sets the length of a vector. So let's dig into these functions in a little more detail. We'll look at the sequence function first, the seq function. We've seen that we can use the colon operator with a couple values like this to generate a vector with the range covering all the intermediate values between the first starting value and the ending value here, inclusive of those values. And here we're using the combine function to manipulate that by adding a few extra numbers to it. But this is fairly limited because you just get these sequential ranges. The sequence function provides more options. You have a from argument, which is where you start. You have a to argument, which is where you end, so nothing new there. But then we have this by argument, which allows us to specify an increment or a step value. So here you see we're specifying a step value or a by argument value of 3. And so we start from the starting value, we end on the ending value, but we increment each one by 3 for our resulting vector. Now these are named arguments. If you know the function well enough to know the order, you don't need to specify the names. This is from, this is to, and this is by, and you get the same result. So it's kind of a shortcut. And then there's the ability to step backwards with a negative step value. Now for this we have to modify the from and to arguments because we can't go backwards from 3 and get to 27, so we have to switch it, and we're starting at 27 and working backwards till 3 with a negative 3 step value. We also have this length.out argument, which is very useful here. We're specifying a starting value of 3, an ending value of 27, but we're not going to go with a standard increment of 1 or any step value at all for that matter. We're specifying the number of values in the range. So starting from 3 and going to 27, we want to have 40 intermediate values in that range. Now, I don't want to do this math, but it would basically be the difference between 27 and 3 divided by 40, but R will do it for you. So you see here, now instead of integer values, we We have floating point. We start at 3, we end at 27, but we have all these intermediate values that are stepping with an equal increment that R has done the math for. So we're adding about 0.6 and about 0.6 and about 0.6 to each value as we work our way up to 27. So this is another option to the sequence function that we can use with that length.out name. Let's look at the replicate function, or REP. Replicate will repeat a value. The value can be a single scalar type number, or it can also be a vector. So we've got some examples here. We're looking at replicating the value 1. The named argument for the value to repeat is x, and then we have the number of times we want to repeat it. By default, it's just 1, which isn't very interesting, so we want to specify something greater than 1. So here we're repeating the number 1 4 times. If we want to specify a vector, we can do that as a call to the combine function, or we can also use a variable here that's already been set with a vector. And again, the named argument x, and then the number of times to replicate it. So here we see 3, 62, and 8.3. You notice it uses floating point because even though the first and second value of the vector are integers, the third is a floating point, so it's going to upcast the other values to the floating point type. And then we repeat the second time, and then repeat the third time. There's another named argument here for the replicate function called each. This one will actually repeat the value in the vector a certain number of times, as well as repeat the vector a certain number of times. So here we're telling it to repeat each value in this vector twice with the each argument, and then we're telling it to repeat this duplicated copy of the vector 3 times. So we'll see 3.0, 3.0, then 62 twice, and then 8.3 twice, and then we start that duplicated vector over again, and then the third time here. This function will take care of some of the menial labor when you're replicating data. The sort function will sort vectors, and so we are using the argument again. X is a named argument, and the function call is sort, specifying a vector here, then the order with a decreasing named argument. And you notice we're setting it to false, which says give us an increasing sort result. So we start at the lowest value, which is -10 in this vector, and we increase up to 3.44. You can also use the shortcut F for false. Anywhere in R where you see false, the keyword, we can use the letter F, and it'll replace it that way. You notice also that we're specifying the arguments in the order that they normally occur. If we want to change and go with a decreasing sort, here we're specifying a vector, and we're decreasing, and so we start with the highest value, we go down to the lowest. By default, decreasing is false, so if you don't specify it, you're going to get a increasing sort order. So if we play around with these functions a little bit and do something like v is replicate, and let's give it a vector c 2, 4, 6, and let's do times equals 2, and v gives us 246 and 246, and then we can sort v, and by default, remember it's increasing. That takes all the elements in that replicated vector and then sorts them in the appropriate order. And then I can do a decreasing sort, of course, sort v, and decreasing equals t for true, and you see we get the same vector elements in a decreasing order for this one. And then finally, the length function. We discussed this earlier. This returns the length of the number of elements in a vector. And so using the colon notation, 5 to 13, we're going to get the values between 5 and 13 inclusive, and that will give us 9 if we spell this out by explicitly typing it in, 5 through 13, and you see 1, 2, 3, 4, 5, 6, 7, 8, 9. For the length there. And then we're doing an interesting little combination here. We're taking a vector with the contents 3, 8.3, and then the replicated number 32 4 times, and then the sequence from -2 to 1. So we're going to get quite a few values in here. So you get 3, which corresponds to here in the vector, then 8.3, and here's those 4 replicated 32s, and then we have the sequence, -2, -1, 0, and 1. So this gives us a length of 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 elements. And what if we took this one step further, and I will type in V. Actually, I could just copy and paste this from the slide, so I don't have to type it all in. So here's V, and then what if we were to say sort V? That will sort it by default in increasing order. You notice we can embed these function calls inside another function call. The C is a function call to combine, and so we can go even further. We could say sort, and then this expression, continue it here. It wants the extra parenthesis here, and then we get the sorted value. So I copied and pasted the other operation in its entirety here, but because I'm putting it inside the sort operation with a left paren, I need to add that last paren. So to do this correctly, I might have just plugged in that extra parentheses after this one, but R just gave me the opportunity to do it with the plus sign here. So once I did that, you see you get the sorted expression. And then if we want to do the result in the reverse, I'll just do my up arrow to bring in the old command, and now I'll add the parentheses, but I also want to do decreasing equals true. But do I need to do this? Remember, we can use the order instead of the named argument if we're familiar enough with the function. And here I'm specifying true, and you see now I get the decreasing sort order. So a few different ways to do this. These expressions can get very complicated, and so using an intermediate variable like this is probably going to make your code more readable. So this is what I would recommend in this case, is to create an intermediate result and then manipulate that result. Now, one thing you might have noticed is that as I'm typing in these commands, for instance, the replicate command here, and providing a named argument, I did not provide the S on the word times, even though the actual argument name, if you look at the help command for the rep function, you'll see that times is the actual name, but I left the S off. This is actually my own error in that I did not type it in completely, but it didn't matter. It worked anyway, and that's the behavior of named arguments in R, is you don't have to specify the entire argument. I could even shorten this more as long as R recognizes it uniquely as a named argument. For instance, I could say PI equals 2. I could say T equals 2. I can put this in front, T equals 2, comma, then the combined vector command, and that works. Whereas if I just try to type it in without the T, I get an error. And so you can shorten these named arguments to the point where, as long as R recognizes it as a unique name in that function, it will work. And of course, we could always just do the ordering if we know the order these things occur in, and then just 2, and that works. But a lot of times it's better to be explicit when you're specifying these arguments. It makes your code more readable. Now let's look at subsetting and element extraction. From your Intro to Programming course, you should be familiar with arrays and how we access an element of an array using square brackets. That will help you in R subsetting. If you've encountered Python's data science libraries, you'll see a lot of similarities in how R behaves here. One of the big differences between other languages and R is that R is one base for their indexes. So that's a key point you need to keep in mind as you work with some of these operations. We normally have arrays that start with element 0. In this case, our vectors and other data types that are collections like vectors in R begin with the index 1, not 0. When we do simple commands, for instance, when we do a range specification here for a vector with the values 5 through 13, and we run the length, we get a single scalar type result back from that length function, and you see here we get 9, and you notice it puts the index of what is internally actually a vector in the results. And so if you wanted to treat output from a command like this as a vector, this would serve as the index. So here we're doing the sequence command from 3 to 27 with 40 values again, and this isn't showing all the data, but you notice that the first element, if you look at this as a vector result, is 3, And here's the sixth element, so 1, 2, 3, 4, 5 on the first line of output, and then it indicates the index for the sixth element. This is helping you in seeing the count of the elements that are returned, but it is actually an index into this vector of output results. So knowing this information can help us extract pieces of our data from our vectors and other data structures. And this is called subsetting. So here we're creating a vector called V with the values 10, 20, 30, and 40, and we're accessing the first element, so V sub 1 in square brackets, just like an array, and the element is 10. V sub 4, 4 in the square brackets, that's the fourth element here, and that returns a single result of 40. If we can take it a little further here, we're going to create a vector called VS, which is month names. We have January, February, March, and April. First element, as before, is January. Third element, 1, 2, 3, is March. Here's an interesting way to get the last element of this vector. The length of this vector is 4, and so we're calling the function length, which will return 4, and we're putting it in square brackets, and then we're accessing that element, and this returns the fourth element, the last element in the vector. We want to do it relative to the length. We're subtracting 1 from the length here, and that's the third element, so that's March. I mentioned already that our vectors are 1-based and not 0-based. Many other programming languages use 0-based arrays. Fortran, an old scientific and engineering language, used 1-base arrays. A lot of math and statistical concepts use 1-based vectors instead of 0-based, for instance, in linear algebra, and so R is no exception to this. It follows that approach. If you try to access an element that doesn't exist, here we're looking at the 0th element of that month name vector we saw on the previous slide. There's nothing there. Now, in other languages, trying to do this might actually crash a program. In Java, this would return an exception if this is an invalid array reference. But in R, it's just saying, yeah, nothing useful here. But you still want to avoid doing this because it could obviously impact your results if you're doing data analysis and doing any sort of aggregation or manipulation of the data to be accessing a vector element that doesn't exist. We can get even trickier with our indexing and our extraction here. We can use negative indexes where we have our month names vector, January, February, March, and April. And now instead of including elements, you're excluding things from the vector. And so here by saying -1, exclude the first element. So we don't see January in this result. Exclude the last element. We don't see April in this result. There is no -5th. So R gracefully just says, there's nothing to exclude, so I'm going to give you everything again. When we use this notation to extract elements, we're not modifying the vector, but if we want to save the changes, save the new subset, if you will, we can assign it to a new variable to save those changes. So here, for instance, here's our month names array again, and we are extracting the third element. So we're going to leave March out of it, and we're assigning it to this new VS vector. So you see the results here. There's no March in that list. Now, if you want to modify the original, you can, but you have to be careful here. So what I'm doing is I'm backing up the original month name vector. I'm calling it old VS and assigning it to VS. Now I've created a new copy of that original vector, and now I can modify the original, eliminate the second element, which is February, and now I've modified that original vector. We can use vectors as indexes. So in these examples above here, you see I'm using a single value in the square brackets. Single value in the square brackets. What happens if we use a vector as an index? Or here's our month name array. Now we're specifying as an index a vector consisting of 2 and 4, which means we're going to select the second and fourth elements from that names array. Now it's February and April, the second and fourth element. The third and fourth, same way, nothing really different there. Do the same thing with the numeric vector we had before called V by extracting the third and fourth elements here, and we get the results 30 and 40. Remember, we can create a sequence with a colon operator, and we can use one of the sequences similar to a vector as an index to a vector. So here we're saying select the first through the third. So we're going to get the sequence 1, 2, 3. So we're going to select all 3 of those elements. or select the sequence 2, 3, and 4 from the month names array, February, March, and April. So you see the difference here between the vector. We're not creating a range of values here. The vector is just those values. But on this slide, we're using the actual range, and so we get a larger number of elements resulting from that because of that range. We can take it even further here, use the replicate function to repeat selections. So we're using the combine function to create a vector of the value 2 3 times. So it's going to be 2, 2, 2, and then 3, 4. And so you can see using this in the square brackets for our month names array, we're selecting February 3 times. 2, 2, 2, and then 3 and 4. Excluding multiple items, put a negative sign in front of the vector. So this says exclude the second and third elements, February and March. And the result is January and April. Have to be careful though, don't mix negative and positives inside that vector, because you're saying exclude and include, and R doesn't like that. You'll get an error if you try to do that. We can use our assignment operator where we're using indexing. So here we've got a vector V, 10, 20, 30, 40. We're changing the first element. And again, this is very similar to how it works in arrays in other languages, except for that one base instead of 0. V sub 1, which is the first element, we're assigning it to 5, and it replaces in the original vector the 10 with the 5. And we can take it further, of course. Here's a vector saying replace second, third, and fourth elements with 10, 15, and 20. Now you have to make sure they match in size. This vector of 3 elements and this vector of 3 elements. And so you see here we've replaced the remaining elements in this vector, 5, 10, 15, and 20. R provides what we call vector-oriented behavior, which allows us to do things with vectors that are going to be very efficient, very powerful, really. And you'll see, again, something similar to this in the Python data science libraries. So here's what we have in R that we can do using the vector-oriented behavior. Our vector is 5, 10, 15, and 20, this vector V. We're going to say add to each element of V a vector corresponding in size with these values. So it's going to add 10 to 5, it's going to add 20 to 10, add 30 to 15, and add 40 to 20. And so here's the resulting vector. You notice we didn't modify V, we just showed the results here of that operation. Using a multiply here, multiply each element of V, so we don't have to specify all the elements of the vector. R will do this internally for us. This is just saying double each element. So multiply 10 by 2, 20 by 2, 30 by 2, and 40 by 2. This is actually more manually intensive than it needs to be. R can be even more efficient using something called recycling. So this is where we're working with 2 different size vectors. What happens is when R gets to the end of a vector that it's operating on with a vector that is shorter, R is just going to recycle it or repeat it. Here you see we've got a sequence from 1 to 6, and this is just a temporary vector. We're not saving it to anything. And we're adding the sequence 1 to 3 to that first sequence. Now there's 6 values in this one, there's 3 values in this one, so we're going to run out when we hit 3. It's going to add 1 to 1, and 2 to 2, and then 3 to 6. So that's the first 3 of this second vector. Now we're out of values. So what do? It starts back at the beginning. It says, okay, start with 1 in this sequence and add it to 4, which gives us 5. Then 2 gives us 7, and then 3 to 6, which gives us 9. So this is just an expansion of the operations that are going on here. 1 plus 1, 2 plus 2, 3 plus 3. Then it recycles that second vector. 4 plus 1, 5 plus 2, 6 plus 3. So it repeats the shorter vector to match the length of the longer one. And this is called recycling. What happens if you don't have a multiple in that second vector? So in other words, 6 and 3, well, 3 is half of 6, so that's easy to recycle. But what do you have? 1 to 5. Not a nice match there. So we get 1 plus 1 is 2, 2 plus 2 is 4, 3 plus 3 is 6. Now we recycle. 4 plus 1 is 5, 5 plus 2 is 7. Now we got that remaining 3 left over. R gives us a warning. Longer object length is not a multiple of shorter object length. So it does things correctly, behaves as expected, but we're missing that last 3 for the recycling operation. So R just lets us know that there's something kind of weird going on there. So here's where I said that doing the explicit multiplication element by element is more work than we need to do, because R is smart enough to say you've got 4 elements in this vector V, multiply by 2. In other words, double each element. We don't have to specify every element here. We're using recycling, and it's basically going over all 4 elements and doubling it. So V is 5 times 2, and 10 times 2, and 15 times 2, and 20 times 2, based on these original values up at the top. So recycling helps us make our vector-oriented behavior even more efficient when we're doing these operations. So we can play around with this a little bit. Let's clear this console and do V, give it some color names, red, green, blue, and let's just do some simple subsetting here. V sub 2 is green, V sub 3, V sub 1, comma 3 to extract the first and third element. Oh, you notice I missed the combine function there. So V C 1, comma 3. And then I can use the range. V 1, 2 gives me red and green. Let's eliminate some. Let's do -1 to get rid of red. Now let's try the negative range, or the negative vector, to eliminate values. -C 1, comma 3. That eliminates red and blue. We'll do some mathematical operations. Let's do vector D with floating point values of the 0.0, 3.5, 10.1, 20.2. And if we do D times C, let's just do some multiplication here, 2.0, 2.0, 2.0, to double each value using the explicit vector-oriented operations. It doubles each of those. Let's make it a little simpler. Let's do recycling, D times C 2.0, 2.0, and you see it recycles, so it gives us the same result. Let's do D times C 2.0, 2.0, 2.0. This should give us our warning message. Remember, not a multiple of the shorter length, so that's expected. And then finally, let's just use the simple recycling to double this, D times vector containing just 2, and it does the right thing. And we can make this any value. Let's multiply each of them by 10 instead. You see that we've got some interesting things we can do this, and I can paint these D C of 2 and then add 3. So this doubled each value. We started with 1, 3.5, 10.1, 20.2. So it doubles them first. So 1 goes to 2, and then it adds 3. And then 3.5 goes to 7, and it adds 3. 10.1 goes to 20.2, and it adds 3. And then finally 20.2 goes to 40.4, and it adds 3. So there are some good examples of using the vector-oriented behavior and the recycling behavior using subsetting and extracting for elements in R. Okay, so now let's start looking at some of the multi-dimensional collection objects in R, like matrices and arrays. So a matrix is a two-dimensional object. I'm going to try to avoid using the term array because we'll find there are a lot of differences here. The description is usually as an M by N matrix, where M is the number of rows and N is the number of columns. And this is just like an Excel table where you have the numbers for the rows going down the left side of an Excel spreadsheet, and the columns as letters in the case of Excel, going across the top. The size of the matrix is m times n. In R, we can index each individual element with two values, the row and the column. And so if we have, for instance, a matrix named A, uppercase A, with the dimensions m by n, then the first element, remember we're using one base collections instead of zero, the first element in the matrix is A1, comma 1 in square brackets. Second one is 1, comma 2. That's row 1 going across the top, column 2. And then all the way up to the number of columns, A1, comma n. And then moving down, second row, first column, second row, last column, all the way down to the bottom right where you have last row, last column for those elements. To create a matrix in R, we use the matrix function. We specify matrix and then our data. Now you notice we're creating a two-dimensional object using a one-dimensional vector here. Data equals combine of these values. And matrices in R, matrices being the plural, matrices in R are kind of a special object. They are internally not really two-dimensional. It's just the way we're displaying them, the way we're representing them, that makes them two-dimensional. We're organizing the data in a different way. So we're using this one-dimensional vector, 3, 2, 893, 0.17, and we're saying organize our data as a two-row by two-column matrix. In row for the number of rows, in col for the number of columns. And again, named arguments, if you do them in order, you don't have to specify the name. This is the result when we display A. We have the rows displaying as 1, comma, and 2, comma for the element numbers, and the columns as comma 1, comma 2. So you notice the comma is after the row index and it's before the column index in those square brackets. And then we have our two-dimensional array, 3, 2, 893, 0.17. You might be looking at this and saying it's going down. It's exhausting the first column and then the second column with the second pair of values. And that's a good observation. We'll see that we can modify this behavior, but this is the default way it fills in our matrix. If you leave the dimensions out, then R defaults to a single column. So here we're using the same data. We left the in row and in col arguments out, and so we get the 4 rows, but it just defaults to this single column. If you specify the data and the dimensions, you need to make sure that your data vector has enough values to fill those dimensions. So here we're specifying the matrix. We're giving 3 values instead of 4. We're saying we want a 2 by 2 matrix, but it can't do that with 3 values. And so we get a warning that we don't have the correct number of multiples. Now, interestingly enough, I'm not printing out the result here. Let's try this and see what we're getting. So I'm just going to copy and paste this from the slides. And create the matrix. There's our warning. So if we display A, what is it? Look what it did. It looks like it recycled that vector. So we had -3, 2, 893, and then it recycles and goes back to the first one, -3. If we want this behavior, then fine, but it's probably not what we want to happen. So you need to make sure that your data vector is the correct size to handle the dimensions of the matrix you're asking for. So I was talking about the way that R fills in the matrix. By default, it is column-wise, or column major. So if we don't specify anything, we get 10, 20, 30. So 10, 20 fills up that column, then 30, 100, 200, 300. It keeps going, 100, 200, and 300. Now there's a by row argument. So I mentioned we can change its behavior. By default, this by row argument is false. So if I explicitly specify false here, you can see the result's the same. It's using the default value and filling in a column-wise order. If I change that to true here, you'll see that it changes the ordering, the way it fills in the matrix. 10, 20, 30, and it's going across in the rows before it starts on the next row. So it's filling in each column of that first row and then going down to the next row. So this by row equals T argument will change the fill behavior of the matrix command from its default column-wise to row-wise instead. So we've seen how we can use the matrix command to create a matrix. We can also create matrices in a more incremental fashion by using the rbind or the cbind functions. These will take a series of vectors, and then depending on if you use rbind or cbind, it will bind, which is effectively like a concatenation operation in the case of rbind of a row by row concatenation of the vectors that are specified. So here we're specifying two ranges, the numbers from 1 to 3, and then the numbers from 4 to 6 using rbind. So it's going to bind on a row-wise operation, the first range, 1 through 3, and then the second range. And it's going to create this 2-row by 3-column matrix. We can also use cbind, which is going to go in a column-wise fashion to concatenate, if you will, vectors using the arguments provided. A combined vector of 1, 4, and then 2, 5, and then 3, 6. So we get 1, 4, and then remember it's column-wise, 2, 5, and 3, 6. And so now we have another 2 by 3 matrix, but we created it in a different fashion with cbind. A lot of times we need to find out information about our object in R, and matrices are no exception. So if we want to find the dimensions being the number of rows and the number of columns, we have the dim function, dim, which returns the dimensions of the object that's passed in. So here we're using rbind to create a matrix of 3 rows, and each of these is a range of 3 numbers, so it's going to be 3 by 3 matrix, and we're displaying it here. And then just to check ourselves, we can call the dimension function with the matrix we just created, m, and display 3, 3 for the number of rows and columns. In a similar fashion, we can use cbind. Now in this case, we are creating a text-based matrix instead of numeric, and we're using the columns with the vectors x, y, and z, and then pitch, roll, and yaw. And this is M2, and then we display it, and you can see X, Y, and Z. This is cbind, so it's a column orientation, and then pitch, roll, and yaw. And then we call the dimension function with it, and we see it's a 3-row by 2-column matrix. If you just want to check one dimension instead of both dimensions, you can call incol, which stands for number of columns, and nrow, which is number of rows, to get the column and row dimensions. So rbind, we're binding 3 rows, 7 to 9, 6 to 8, 5 to 7. So 7 to 9, 6 to 8, 5 to 7. And we're calling dimension, passing the matrix and seeing it's a 3 by 3 matrix. And then we call incol with that matrix to see it's got 3 columns, or nrow to see that it's got 3 rows. Now you notice we can use a bracketed index here to extract just one of the dimensions returned by the dimension function. So we're using dim m, which is going to return 3 by 3, but we're saying just give us the first element of that, because dimension is actually returning a vector of 2 numbers, the number of rows and the number of columns as a vector. And so we're just specifying show us the first value from that, and we get 3. Now let's look at extraction and subsetting with matrices, which is similar to vectors, but you've got to work with the extra dimension. So if we've got a matrix, this is an earlier matrix we generated using rbind, if you look a few slides back, with these values 7, 8, 9, 6, 7, 8, 5, 6, 7. If we use the 2-dimensional indexing scheme for extracting a single element, so this says give me the second row, the first index is for the rows, second is for the columns. Give me the second row, second column, which is the middle number here. And then for 1 and 3, row 1, column 3, this is an error. I need to fix that. It should be the third column. First row, third column here is 9. And then if we don't specify the second dimension, in this case we're just specifying 2 for the row number, R is going to default to the first column. And so first column for the second row is 6, and so that's the result we get here. So let's play around with this. I stole the rbind command we used to create the matrix M back from the previous slide here, and I'm just going to copy it and then paste it into my console. And so now we have M, those values, and some simple expressions. M 3, 3 is going to give us the third row, third column, and M let's say row 1, comma, column 2 gives us the 8 from this value. And then if we play around with just specifying the row, remember it defaults to the first column, so I'll do M sub 1, and here's 7, and M sub 3, and here's 5. Try to do an invalid index. Let's try 0, 0. You can see we don't get a real result from that. And let's do something that's on the other side of the bounds. Let's do M4, 4, and then we get an out of bounds subscript. So a little bit of difference in the behavior of R if you go too low for the index versus going too high. If we put the comma first, then R interprets this index value as a column. Now the comma is required for this behavior, otherwise it assumes the row and defaults to column 1. So this is specifying give me the third column. So over here you see 987, and that's the result I get here. Here I'm saying I want the entire row. Now look at the difference here. By putting the comma in there, I'm telling R I want the entire second row, 6, 7, 8. Look at the previous slide where if we specified a single index without the comma, then it defaults to column 1. So there's an important difference how the extraction occurs here in these examples. Make sure you pay attention to the difference in behavior here. We can do some basic extractions that we've seen, and we can actually create a new matrix using more complicated expressions. So remember our range operator, the colon. This is saying give me rows 2 through 3, and then we don't specify a column. We're going to get the entire row for each of those index values. And so you see we get row 2 here and row 3 here, but now this new matrix is 2 rows by 3 columns instead of 3 rows by 3 columns. And if we wanted to assign this to a variable, it would save the result and we would have an entirely new matrix created from the original with this extraction. We can get fancy. We can extract diagonals. So we have this 3 by 3 matrix where we have 7s on the diagonal. And if we call the diag function and pass the matrix, it gives us those values. And when you do matrix operations, a lot of linear algebra and some other types of math need diagonals. And so this is an important operation that we can do. Here's a text-based matrix, 3 rows by 2 columns. If you remember, we did the C-bind to create this one. So the first column is X, Y, and Z. Second is pitch, roll, and yaw. We're calling for the diagonal, so the diagonal here is going to go just through the first 2 rows because it's not a square matrix, so there is no third row, third column here. So it gives us what it has. So it's kind of a subset of a full square matrix diagonal, but it is the diagonal for this particular 3 row by 2 column matrix. As with vectors, we can omit elements with negative indices. So here's M again, and we want to remove the third column. Remember, the negative index removes an element, or removes multiple elements in this case. And so we're saying in every row, because we're not specifying the row, but we're using the comma, in every row, remove the third column from the matrix. So we have 765, 876, and you see that it cuts this entire column out by doing that removal. Get even more complicated here. Remove the first row and extract the third and second column in that order. So we're going to use the multi-dimensional index here, and we're going to specify -1 to remove the first row, and that would be 789. And then we want to extract the columns, and we're specifying the range in a backwards order. So we're going from column 3 to column 2. And so we get 8, 7, that's column 3, as the first column in this new matrix. And we get 7, 6 as the second column in this new matrix. So these can get kind of tricky. They can get pretty complex, but you'll find as you get better at them, the ability to do this kind of thing can make your coding much more efficient. As with vectors, we can assign new values to existing elements. So we've got M2 here, 3 rows by 3 columns. We want to assign a range of values to row 2. In other words, we want to replace the entire row 2's values. Using the assignment operator, you can see that we are saying use the second row, providing the comma, So it's going to use all the columns instead of defaulting to one, and we're assigning the range. And we need to match our values unless we want recycling to occur. So we've got 3 columns, so we're using 3 values, 10 through 12. And you can see here that it has replaced those values. Now you notice it does it in place. We're not assigning this to a new variable. We have just modified our M2 when we did this operation. So if you want to preserve the original, you might copy, just do an assignment to a temporary variable here to store the old M2, and then do this modification. And I mentioned that if you want to use recycling, you can on these. And so here we're assigning 10, all 10s to row 2. And so we specify row 2, and by giving it a single value of 10, it's going to recycle that value across all the columns. So this 10, 11, 12 becomes 10, 10, 10 in our new matrix. So recycling works with matrices in a similar way that it works with vectors. Now remember that matrices fill column-wise by default. So for this example, we're using vectors as our index values. So our vector C1, 3 is our row index for this replacement operation, and our vector 1, 3 is the column index. So you notice the replacement, we're taking row 1 and row 3 and column 1 and column 3. Since we're using the column-wise default, we're going to do row 1, column 1, followed by row 3, column 1. It's moving its way down to assign those values. Same thing in the second one. It's taking now row 3 and doing 99 and 11 for column 3. So now we'll talk about arrays in R. I've been mentioning how vectors are similar to arrays in other programming languages, and matrices are similar to two-dimensional arrays in other programming languages. But by specifying the actual array type in R, it's giving us some special additions to that data type versus just storing values of a specific type in that data. We're actually going to be able to apply other attributes to those data structures as well. In particular, we can provide names for the dimensions or data structures. If you look back at the matrix output here, you notice our columns are just using numbers and commas and square brackets. And our rows are using numbers and commas and square brackets. We might want to give these more meaningful value instead of just those numbers. So an array is 1 or 2 or even more dimensions. A matrix, remember, is 2 dimensions. A vector is 1 dimension. So the one-dimensional array is like a vector, but with these additional attributes. A two-dimensional array is like a matrix, but with these additional attributes. And arrays are dealt with differently depending on the operations you're performing with them. So let's just jump into the multiple dimension aspect of arrays and show how we can use them. So let's do a 3D array, and we're going to use the array function, no surprise there. Fill order is column-wise, as with matrices. And we're going to specify the data for the array and the dimensions. So this is similar to matrices, except we're able to add this extra dimension. We're adding a third dimension on this one. And so I'm going to fill it with a range 1 through 24. And the dimension is going to be 3 by 4 by 2, which means 3 rows, 1, 2, 3, and 4 columns, 1, 2, 3, 4. But you notice we get this extra block of values over here. And actually the third dimension is known as a layer or a slice. So now we have, if you count them, we've got 3 by 4, which is 12, plus 3 by 4, which is 12, so that's 24 total. So there's our range. Start at 1, go through 12 for the first slice, and continue in the second, 13 through 24. So that's all 24 values. So this is just displaying the basic 3D array. When we extract rows from the array, we get them as columns. So this is different behavior that you need to be prepared for when you see it. We created this array called A with the 2 slices here, 24 values. Now it's specifying, give me row 2 of the array A. Remember, you've got multiple layers of data here. You've got a row 2 here, and in the second slice, you've got a row 2 here. And so R gives us this output in a column-wise fashion, where row 2 from the first slice is here, That's 2, 5, 8, and 11. And then row 2 from the second slice is here, and that's 14, 17, 20, and 23. We can go even further with more dimensions. We're going for a fourth dimension here. So we're doing an array, and we've got our standard 1 through 24 for our range, but we're using the replicate function to give us that value 3 times. And if you notice here for our dimension, we're saying 3 rows by 4 columns by 2 slices by 3 blocks. So the fourth dimension here, we're using the term blocks to describe that. And so this is our previous result, the 2 slices with the 3D array, but you notice we've added another dimension here. It's the first block. So these 2 slices of data comprise the first block of the 3 blocks that we're going to be providing. And you can see it goes from 1 through 24, just as before, but now you got to go to the next slide and see. Now we've got another block, and here's that third block. So we've got 72 total values. The second block starts at 1, ends at 24. Third block starts at 1, 24. So this is the way we can do these multi dimensions for our arrays. How often you come across these, I would say not that often, because we're going to get into more useful data structures called data frames that actually kind of are derived from arrays. And we'll see how we specify the dimension names and do all the useful stuff with those when we get into them. If we want to extract elements from a multi-dimensional array, it's the same as before, same as you expect, but you got a bunch of numbers, and you make sure you do the right number of columns. This gives us the single value, the single element value, row 2, column 2, slice 2, block 2, which just happens to be 17. If we look back up at our data, the second block, slice 2, and row 2, column 2 is that 17 there. And then you can use the same tricks as we did with matrices by leaving the values out but including the comma. This says give me the second row, second column, second layer of each block. So second row, go back to the first block, second row, second column, second layer. So that's going to be in here. Here's second row, second column from the first block, then from the second block, and then from the third block. And so we're saying give the value corresponding to that location from each block. So we'll get 3 of them. Here's another example, and you notice here the result is going to be a matrix. So it takes that 4-dimensional array, and we're extracting a 2-dimensional matrix from it. It says give us a second row, second column of each layer or slice of each block. So we get 5, 5, 5, 17, 17, 17. Look at our data. Here's the first block. We get 5. And second block is 5. And then third block is 5. And then we go back and we get the second row, second column from the second layer. 17 and 17. And then 17 over here. So those are examples of how we can do extractions from these multi-dimensional arrays, similar to matrices, but with more dimensions. The last thing to show here is a simple example of naming the array dimension that we have the ability to do in R with the array object. I'm going to show you a 2-dimensional example similar to a matrix just to keep things simple. And arrays aren't the most commonly used data structure in R. We're going to get into data frames, as I mentioned in the next module, and we'll see that it works in a similar fashion for data frames, and so we're going to cover it in more detail there. But just to show you an example of how it does work, creating an array here, and this is going to be a 3x3 array, so I'm specifying the range 1 through 9 for my values. Here's the dimensions. Now for the dimension names, I'm using the dim names argument, and we're using a list. A list is yet another type of data structure in R that we will talk more details about, but let's just say that this is going to be more or less a bucket to put our dimension names in for this array. So I'm creating a list with this list function, and I'm using 2 vectors. One contains the names for the rows, and one contains the names for the columns. Just simple row 1, row 2, row 3, column 1, column 2, column 3. Separate vectors. Got to watch the parentheses here. There's a lot of them. If we had more dimensions to this array, we could include more vectors for the names of those dimensions, for the slices and for the blocks. And you can see when I display the contents of this array, instead of using the numbers in commas in the square brackets, it gives us our names, column 1, 2, 3, and row 1, 2, and 3. And so if this were real data, we could give them names that would mean something to us and understand what we're looking at. The row naming is probably less common, but the column naming is definitely critical because we'll be naming our data with field names, where every column is a field, similar to a database. We'll be using this naming feature pretty extensively when we get into more complex data types.